So with section 8.3, it says reactions in aqueous solution. A lot of this, or the beginning of it at least, you've had. It's basically double replacement reactions that we're going to look at in a little bit more detail. So now this slide says molecular, complete ionic, and net ionic equations. So there's three like subtypes of equations that you're going to have to write for these double replacement reactions. And I'll say this molecular equation right there, we've been doing that all along. You've been writing molecular equations all along, predicting the products, getting the equation balanced, all of that good stuff. So that's nothing new, but this complete ionic and net ionic is going to be a little bit new. Okay? And basically it's going to be two examples we're going to do for notes, and then I'm going to probably do one reaction just to show you here, and we'll be done. So this one, you want to write this one whole problem out here, and then we'll have one more where you can put quotes for most of this stuff. So write this problem out in your notes, and I'll give you a minute or so to do this, and I'll get some other things ready. While you're finishing up with this note here, hand your labs in. And then also, if you're finished or finishing up with this, you're going to need table 8.3, just write it right here, which is on page 227 of your textbook. Turn to table 8.3, which is on page 227, another table that you're going to have to know how to use, not memorize, but know how to use. So I'm going to give myself a blank page to write with this. I got to look at what we need again. So potassium carbonate and calcium chloride are mixed, we need molecular complete ionic and net ionic equations. So there's 3 different types of equations we're going to write. The molecular, again, is what you know how to do already. The complete and the net aren't too much more difficult. We're going to want to include physical states for everything. All species means all chemicals. So physical states, all liquid, gas, aqueous, all that stuff. And then this precipitate and spectator ion stuff, I'll talk about that as we go. It's not too difficult. And then the type of reaction. Okay? So the first thing, we have calcium chloride and potassium carbonate. So I'm going to write those formulas. And actually, I know there's calcium and calcium chloride, and I know there's chloride, but you don't just write that down and say, okay, that's my formula. Because you have a metal, Ca, you're going to have to work with charges. So what's the charge on Ca? 2 plus. What's the charge on Cl? 1 minus. And then you crisscross those charges, remember. So it's going to be 1 calcium and 2 chlorines. So it's Ca. Cl2 is our first reactant. Okay. Plus, the other one was potassium carbonate. So I know there's potassium in there, which is K. What's the charge on K? As an ion. 1 plus. It's a metal. And then carbonate. What is carbonate? CO3, what charge? 2 minus. So I'm going to write that down. And this will help if you're writing your little notes to yourself in a problem just like this, because you can use this throughout the whole problem. So then again, you crisscross it, so it's going to be 2 potassiums and 1 of these carbonates. So it's K2, CO3, and then arrow. So looking at this, just looking at it, 2 ionic compounds. What type of a reaction does this look like it's going to be? Double replacement. So you can write DR. Usually on a quiz there'd be a line for it, or you write it towards the end, but it is a double replacement reaction. That's an answer, so I'm going to box it out. That was one thing that was being asked for. And then we need physical states. Here's what the 2 chemicals look like. Here's potassium carbonate. It's just a white granular substance. Here's calcium chloride. It's a white flaky substance. If I ground both of these up, they'd both look just like white powders, and they're about the same shade of white as well. So I have those 2 chemicals in these 2 test tubes here. Okay. Looking at those 2 chemicals, what physical state are they? Solid. Don't put solid though. The reaction will never happen if they're not solid, because in a double replacement reaction, you need these ions to be able to move. If I pour them together, nothing happens, because the ions can't move. The ions are locked together right now. Okay? So for example, the potassium ion is locked with the carbonate ion, and the calcium ion is locked with the chloride ion. Okay? It is a double replacement, and in a double replacement, the 2 metals are going to want to switch, or metal and a hydrogen. So this calcium here and this potassium are going to want to basically replace each other. But they can't move. So how can you get those so that the ions can move? Put them in what? Water. So I need to put them in water. And I'm going to do that right now. I'm just going to add not a whole lot of water. I know one of these is going to get really warm. Calcium chloride, it's called an exothermic reaction. So on your left, as you're looking at these, on your left, the one I'm squirting water into right now, that's the potassium carbonate. And then the other one on your right, that's the calcium chloride. And they're dissolving. The chemicals are dissolving a little bit. I'm just going to mix both of these up a bit. And they're pretty much dissolved. They're a little bit cloudy right now, because there's still things floating around. But I'll leave those be in the beaker. Let them dissolve all the way. So what's the physical state of the calcium chloride now? Aqueous. So we're going to put AQ. And the potassium carbonate as well is aqueous. Okay? So it's a double replacement. I'm going to go ahead and try to figure out this reaction. So again, the K right here and the Ca will switch. So now the K is with what? Cl. So the K is with the Cl. I'll worry about charges and formula in just a minute here. And the Ca is with the CO3. All right. Now, I wrote the charges right here before. The charge on the potassium, let's say put a note way up high here, so when I box this out, the little charges aren't in my box because you can't have the charges left. K is 1 plus, a Cl is 1 minus. How many of each of these ions do I need? The K and the Cl? One of each. Okay. The Ca is a 2 plus because we wrote it down right here. And the CO3 is a 2 minus. We wrote it down right here. So 2 plus, 2 minus, those just cancel. You need one of each of those ions. I'm going to make life a little bit easier on myself with this balancing, and I'm going to put the polyatomic ion in parentheses because the same polyatomic ion, the carbonate, is on the other side as well. So now we need to balance these. And you can start wherever, but my eyes are being drawn to this 2K right here. There's 2 potassiums. There's 1 here, so multiply by 2. But now I change my chlorines to 2. If you look over here, your chlorine is already 2. And that, I believe, is balanced. But on these, you need the physical states for everything. So what's the physical state for KCl going to be? That's where table 8.3 comes into play. So looking at table 8.3, the first column, or the second column, look at solubility. There's 2 different words there. It says soluble, and then way at the bottom, one says most are insoluble. What does soluble mean? It dissolves in water. So that's something you might want to write down because it's a question on the quiz, I believe. It's a question on your homework today. Soluble just means something that dissolves in water. So what do you call it if it doesn't dissolve in water? Insoluble. So insoluble means does not dissolve in water. So what physical state would something be if it were soluble, if it were dissolved in water? Aqueous, just like the 2 chemicals I have in the test tubes up there. Or if something was insoluble, what physical state would it be? Solid. Okay. So now what you do, we need to figure out what are the physical states of these 2 products. So I'm looking at KCl. I'm going to look in table 8.3 at the compound list. I'm going to figure out what kind of compound this is based on their category. So the first one says salts of alkali metals and ammonia. Well, I know K is a metal. What kind of metal is it? Group 1 metal, which is called what? Alkali metal. And then group 2 would be called alkaline earth. So this potassium right there is an alkali metal. It's a compound of an alkali metal. It's with chlorine. So according to rule number 1, salt is an ionic compound. So this is a salt. Salts of alkali metals, solubility it says soluble. And there's exceptions. It says some lithium compounds. Well, this is not lithium. So this compound is soluble, this KCl. It's soluble. What does that mean it does in water? Dissolves in water. What physical state is it then? Aqueous. So you have to write the AQ there. Calcium carbonate. What kind of metal is calcium? Which is in group 2. Alkaline earth. It's not an alkali metal. And we have carbonate. So we're looking at something like alkaline earth or else carbonates. So if you look at the list there, the compounds in the table 8.3, 1 has nothing to do with calcium carbonate. 2, nitrates and chlorates. Nope. 3, sulfate. Nope. 4, chloride. Nope. 5, carbonates. This is a carbonate because of the CO3. Okay. So carbonates and a bunch of other things. It says solubility. Most are insoluble. They don't dissolve in water. Exceptions. Compounds of the alkali metals and ammonia. Is Ca an alkali metal? No, it's an alkaline earth, we said already. So this is not an exception. This is insoluble. So what's its physical state? Solid. It doesn't dissolve in water. So CaCO3 is a solid. And this whole equation here, I'm going to write it here, is the molecular equation. I just wrote it off to the side there, kind of scribbled it because I'm out of room. That is the molecular equation. The next equation you're going to want is called the complete ionic equation. I'm just going to write complete ionic, saying that's what I'm doing. And complete ionic is basically to tell what's really going on. So if I take these 2 test tubes now, and pour one into the other, doesn't matter really which one I pour. This one's still a little cloudy, but that's okay. If I can drip it in, I don't know if I can. Is there a reaction happening there? Yeah, for sure. You pour one into the other, there's obviously a compound. It's gelled up like cottage cheese on the bottom there. Okay? So there is definitely a reaction, and that's what we did. We predicted there would be a reaction. If everything was dissolved in water, that means nothing's happening. Okay? This came out a solution. I'm going to underline that now. Okay? I'm going to underline that, and underneath it, just for note's sake, I'm going to write PPT. That's an abbreviation for precipitate. That is our precipitate. The solid thing that is formed, it's a solid, is your precipitate. It's kind of like snow or rain or whatever. It falls to the bottom of the beaker. Eventually this stuff is going to fall to the bottom of the test tube if I let it sit here. Okay? So it asks, what's the precipitate, if any? Calcium carbonate's our precipitate. Okay? What is calcium carbonate? It's chalk. So that's chalk in that test tube, not the white stuff. The complete ionic. Here's the easiest way to think of it. Anything that is aqueous, which is a bunch of stuff in this problem. Anything that is aqueous, you break it up into its ions. Because really in that test tube over there, calcium chloride, it's not CaCl2 stuck together. Okay? It's two separate ions. Or potassium carbonate. When I put it in water, it's not potassium carbonate anymore. It's potassium and carbonate ions. This, the precipitate, it's stuck together. That's why it's a solid. Okay? It's not dissolving. Okay? Dissolving is basically separating the ions. So anything that is aqueous, you break up into the ions. So the first one here, there's a calcium ion. There's only one. Its charge, we wrote it up here. It's 2+. It's an ion, so you have to put the charge. Its physical state, it's dissolved, so it's aqueous. Okay? I'm going to switch pens here. Then the next thing. This is part of that calcium chloride, but it broke away. How many chlorides are there? 2. You do not write Cl2. That's a gas. There wasn't bubbling. It's 2 Cl's. What's the charge on Cl? We wrote it right here. 1 minus. Okay? Plus the next thing. K2CO3. Do we break that up? Yeah, it's aqueous. How many potassiums? 2. Basically, you kind of look for the metal or a hydrogen. So it's 2 Ks. You have to put the charge, though. Its charge was right there, 1+. Plus, oh, I forgot something on both of these. What did I forget? Aqueous. You have to put physical states, it said. So AQ, this is a plus, the next ion. You don't break this to carbon and oxygen. This is the ion. Carbonate is the ion. Each thing will give you 2 ions at this level. So it's CO3, 2 minus, aqueous. And then your arrow. I'm going to run out of room, so here's what I do. You're running out of room to the right, you can do the same thing. I'm just going to write the arrow down here. Now I'll have enough room for everything else. So now I'm on this side. This breaks up because it's aqueous into 2 potassiums, 2K, 1+, which are aqueous, plus how many Cl's? How many Cl's are here? There's 2 because you're multiplying everything in here by 2. So it's 2 Cl's with a 1 minus charge. Again, you have to put the charge. Aqueous. Plus, what does calcium carbonate break up into? It doesn't. That's your precipitate. That's the one that the ions are stuck together and they're not dissolved. So the precipitate or the solid you keep together. So it's CaCO3. I'm going to underline it. I'm going to put S by it. That is called our complete ionic. That is showing everything that is in this test tube right now. All of those ions are in the test tube. 2 of them are sticking together, the calcium and the carbonate. That's the white stuff on the bottom right now. And then finally the net ionic equation. It's kind of like a checkbook. So I'm going to write net ionic here. You pay all the bills and you are left with what you actually have. That's what a net is. So what do we actually have? The easiest way to write the net. A book won't show you this or anything. I write the arrow first. Doesn't mean you have to, but I do. And I look, what did we actually make? What did we actually make? What is this white product that we actually made on the bottom? Chalk, calcium carbonate. Basically, you write down your solid, your precipitate. So we made calcium carbonate. What did it take to make that calcium carbonate? You look on the other side of your arrows, on the reactant side of the arrow. Well, we needed calcium. That was this ion. And we needed carbonate, this ion. And you make sure it's balanced, and you make sure charges are balanced. Okay? Balancing the equation balances the charges, and that's balanced. Okay? So we know what our precipitate is. It's right here, the calcium carbonate. We know our molecular equation. This is normal. We know our complete and our net ionic equation. There's one more thing it asks for. I forget. What did that problem ask for? I think at the bottom. Spectator ions. Spectator ions are kind of like things that aren't really taking place in the reaction, or things that are just watching. Spectators are people that watch. Players are things that are playing. Who played? The calcium and the carbonate played and made calcium carbonate. Who didn't play? All the other ions. Everything else. So the spectator ions, first of all, spectator ions, it's an ion, so that's telling you charge. And you get this from the reactant side. So what isn't in our net ionic equation? Which ions? Looking up in here. Potassium. I don't care how many, but K1 plus is a spectator. What else? Chlorine. You don't see Cl or K1 plus in the net ionic. What else? That's it. And that's basically a point. You identify them all or you don't. So we got our spectator ions, our precipitate, our PPT equals calcium carbonate. I'll just kind of make that clear. We have our three different reactions. We have all our physical states. If you miss the physical state on one of these, basically you lose the point. Physical states is just worth 1 point. You got them all right or it's wrong. Same with each balanced equation then. 1 point each, right or wrong. So this is like a 5 or 6 point problem. We're going to do one more. You don't have to write the whole thing out because from right here, everything else is the same as the previous problem as far as what I want you to do. So just write the beginning up to this green slash there for your example. So this one, solutions of iron 2 nitrate, a new compound, and aluminum chloride are mixed. So I'm going to go back to this. Solutions of iron 2 nitrate and aluminum chloride are mixed. And then the rest, like I say, is it's all the same things we're going to be looking for. So iron 2 nitrate and aluminum chloride. I'm going to go to a blank slide here again. Anybody need this slide still? Iron 2 nitrate, aluminum chloride. What's iron symbol? Fe. Again, I'm going to kind of do notes up here. It was iron 2 nitrate. What does that 2 mean? 2 plus. Iron is 2 plus. Nitrate. What's nitrate? NO3, 1 minus. So you can see you're going to need your ions for this stuff. And then you crisscross. So how many irons are we going to have? 1. How many nitrates? 2. So iron 2 nitrate is Fe. NO3, I want 2 NO3s though. So how do you do that? Parentheses. And then the 2. That's 2 of NO3s. It said, I think it said solutions. Usually it'll say solutions of, that means aqueous. Plus aluminum chloride. So there's aluminum in there. and there's chloride. Aluminum's charge is, from the periodic table, 3 plus. Chloride we had on the previous problem, it's 1 minus. So you crisscross those charges again. So it's Al1, Cl3, and it says solutions of, that means aqueous again. I can write aqueous correctly, there we go. Goes to, what kind of reaction does this look like? Single replacement, combustion, what? Double replacement again. So this is a double replacement. I'm going to write Dr up here, box it out. What we're writing right now is the molecular equation. I'm going to write M period E period, just saying that's the molecular equation we got going on here. It's a double replacement, so usually you're looking at 2 metals or metal and a hydrogen switching. So that's going to be the Fe and the Al that are going to be switching. So Fe is now with what? Cl. And Al is with NO3. We're going to go back. We had Fe already. We wrote it down way over on the left. Its charge was 2 plus. Just going to write a little 2 plus up there. Cl was a 1 minus. Crisscross those, so 1 iron, 2 chlorines. Aluminum, we had its charge right here. It was a 3 plus. Just write myself a note. NO3 was a 1 minus. Crisscross those, so it's NO3, 3. Al1, NO3, 3. Physical states. Let's look at the physical states. How do we tell what state these are going to be? Aluminum nitrate and FeCl2. Table 8.3, page 227. Sorry. Let's take a look on page 227. Let's look at the FeCl2. We're looking at something says about iron maybe, or chlorides, or halides. Is there a note about iron anywhere? Or chloride? 4? Yep. So note 4 says chloride salts. This is a chloride salt. It has chloride in it. Solubility, soluble. Exceptions, always look at those. Compounds of silver, mercury, or lead. This is iron. It's not silver, mercury, or lead. So this is soluble. What's its physical state then? Aqueous. AQ. Aluminum nitrate. You're looking for something that says something about aluminum or nitrate in the rules. And the second rule says nitrate salts and chlorate salts. There's nothing about aluminum, but it does say nitrate salts. This has nitrate in it. Solubility, it's soluble, few exceptions. So this is soluble. What's its physical state? Aqueous. We didn't balance this yet, so I'm going to balance here. I see 2 chlorines and 3 chlorines. I know that's never going to balance. I got to get a least common multiple there. What's the least common multiple of 2 and 3? 6. So what do we do to get 6 chlorines here? Multiply by 3. And we want 6 chlorines here, so multiply by 2. So now we have 2 aluminums. Ooh. Now we need 2 aluminums here, but I just changed my nitrates to 6. So how do I get 6 nitrates here? Multiply this by 3. Now I have 3 irons. 3 irons. 2 aluminum, 6 chlorine. That's balanced. Okay. So the molecular equation is done. The complete ionic. I'll tell you something here. We're going to simplify it. What was the precipitate in this reaction? What's the solid that we made? There isn't one. So what really happens when you mix these 2 chemicals dissolved in water together? If this is an aqueous product and this is an aqueous product, what do you see? Looks like water. So what happened? Nothing. What kind of reaction is this? No reaction. Nothing happens. The net ionic then? I mean, you could write out the whole complete, and when you get to the net ionic, you're going to say, okay, what's my precipitate? There's nothing. Nothing happened with this. So just because you mix some chemicals together doesn't mean that you're always going to have something happen. Doesn't mean just randomly mix things together. But so what are my spectator ions then? All of them. Spectator ions equals everything. all of these would have dissolved up into their ions. What's my precipitate? There isn't one, so I'm just going to write the null symbol. Null, nothing. Okay. No reaction. Just one more slide that you don't have to write anything on here. So the one more slide is this little precipitate in real life called calcium oxalate dihydrate. Sounds like a crazy compound, but it's a pretty simple compound. Otherwise known as kidney stones. Anybody know anybody that's had kidney stones? I know some people. Are they painful or are they not so painful? Sounds like they're painful. That's graph paper. So that's the size of the kidney stone that this particular person had. How'd you like to try to pee that out? It's not going to happen. Okay, not easily when they get this big. So they basically put you in a tub of water. That's one way. There's surgery, or else they can put you in a tub of water, and then they put sound waves through the water. And what do the sound waves do if you get the right frequency and they meet up at this kidney stone? They shatter it, and then you pee out dust and particles instead of that big thing. Another example is calcium oxalate monohydrate. Similar things. They're both kidney stones, just another form of kidney stone. Here's what this one looks like. That wouldn't be fun. Okay. So that's just I mean, they precipitate in your kidneys basically, where blood is in. What's that? You don't have to write that down. So here's the homework. I try to do the back. It starts on the back. Hopefully show you some